Welcome to the Deep Dive. Today, we're taking a really fascinating plunge into the world of ultrasound physics, and specifically the Sonography Principles and Instrumentation exam, the SPI.
Right.
Our mission, really, is to cut through all the complexity. We want to distill the absolute core concepts and the practical strategies you'll need.
Whether that's for acing the SPI or, frankly, just if you're curious about how we manage to see inside the body using just sound. It's pretty amazing stuff.
It really is.
And we've pulled together a great set of sources for you, covering everything from the real basics of sound waves right up to the evolution of diagnostic imaging today, and even some really effective study techniques.
Exactly. So, yeah, this deep dive is definitely for you if you're a student, maybe getting ready for the SPI, or maybe you just love those aha moments and want to understand the science behind it all.
Yeah.
We're going to unpack some, I think, genuinely surprising facts and try to demystify what can seem like a really intricate field.
Our goal really is to walk you through those essential concepts, show you how the different technologies actually create those detailed images we see, and arm you with some proven strategies to tackle that SPI exam, which, let's be honest, can be pretty challenging.
It has a reputation.
It does. So, yeah, let's get started.
Okay, so let's unpack the language of ultrasound first, because before we can visualize anything, right, we need to get the fundamental physics principles down. Our material points to like 10 foundational concepts that, well, everyone really needs to grasp.
Yeah, think of them as the absolute alphabet of ultrasound. You have to know these letters before you can read the words.
Right.
We're talking about the basic properties of the sound waves themselves. Things like frequency, wavelength, amplitude, how fast they travel, propagation speed, and period.
Okay.
But it's more than just a list. What's really key here is how these properties directly impact the image quality you get.
Oh.
Well, take frequency, for example. Higher frequency gives you better detail, better resolution. But the trade-off is it can't penetrate as deep into the body. So you're always balancing things.
Ah, okay. That makes sense. And then there's how the sound actually interacts with the body tissues, right? That seems crucial for making an image at all.
Absolutely crucial. You're looking at things like attenuation, which is really just the sound signal getting weaker as it travels deeper. It gets absorbed or scattered.
Okay.
And then, of course, reflection and transmission. Those are the absolute basis of every single echo we detect and display.
Right, the bouncing back.
Exactly. And don't forget the transducer itself. The magic, really, is the piezoelectric effect. Certain crystals converting electricity into sound waves, and then, crucially, converting the returning echoes back into electrical signals.
It's kind of amazing that works.
It really is.
Yeah.
And beyond those, you absolutely have to understand resolution, like how clearly can we tell two close together things apart?
Right. Image clarity.
Yep. And artifacts, those sometimes confusing things you see on screen that aren't actually real anatomical structures. They're like optical illusions, but with sound.
Okay. Got to know what's real and what's not.
Precisely. And finally, safety principles, especially a la RAR, as low as reasonably achievable. It's about using the lowest possible ultrasound energy while still getting the diagnostic information you need. Safety first.
Got it.
What's really fascinating, though, is how all these, seemingly abstract physics ideas, they directly translate into the quality and the safety of the images we use every day in clinics. It's not just theory for an exam, it's the foundation of good patient care.
Okay, so here's where it gets, I think, really interesting. And our sources flag this as maybe the secret sauce of ultrasound imaging. Acoustic impedance. It sounds like a mouthful, but it seems absolutely vital. So can you break that down? What exactly is acoustic impedance, and why does it matter so much for seeing things?
Right. Acoustic impedance, often just called Z, it's basically a measure of how much a tissue resists sound passing through it.
Resists. Okay.
Yeah, imagine sound waves trying to push through different materials. Some, like, say, soft tissue, they let sound pass relatively easily. Others, like bone or air, they're much tougher for sound to get through. They impede it more.
Yeah.
Scientifically, it's defined as the product of the tissue's density, how packed together it is, and the speed of sound specifically in that tissue. So Z equals rho times C, density times speed.
Z. Okay. And that formula, how does that connect to the image we see?
Well, that's the key insight our sources really highlight. When an ultrasound wave traveling through one tissue hits the boundary, the interface, with another tissue that has a different acoustic impedance.
Different Z value.
Exactly, different Z value. Part of that wave reflects back. It bounces off that boundary like an echo. and the other part keeps going. It transmits deeper.
Okay, so reflection happens at the boundary.
Yes, and here's the crucial part. The bigger the difference in acoustic impedance between those two tissues, the stronger the reflection, the more sound bounces back.
Ah, so a bigger difference means a brighter echo on the screen.
You got it. That's precisely why we can see distinct structures. Think about the boundary between soft tissue and bone. Very different impedances, huge difference. So you get a really strong, bright echo. Same for tissue and air, like in the lungs. Massive impedance difference.
Which is why air is usually the enemy of ultrasound, right?
Oh.
Too much reflection.
Generally, yes, it creates shadowing. And that also perfectly explains why we use coupling gel.
Right, the gel.
That gel gets rid of the huge impedance mismatch between the air, which is normally between the transducer and the skin itself. Air has incredibly low impedance, skin is much higher. Without gel, most sound would just bounce off the skin surface.
So the gel bridges that gap.
Exactly. It allows the sound to actually get into the body efficiently, so it can create those echoes from deeper structures. It's all about managing those impedance differences to get the echoes you want.
Okay, so once we mastered creating images from echoes, the next big leap seems to have been making those echoes tell us about movement and building, well, richer pictures overall. Ultrasound has definitely evolved dramatically. Let's talk Doppler. It's way more than just a cool sound, isn't it?
Oh, absolutely. Doppler ultrasound uses a really fascinating principle, the Doppler effect. You probably know it from sound, like an ambulance siren changing pitch as it passes you.
Yeah, sure.
Well, same idea with ultrasound. The frequency of the sound waves changes when they bounce off something that's moving, like red blood cells flowing through your vessels.
So the machine detects that frequency shift.
Precisely. And that shift, how much the frequency changes, tells us two key things. How fast the blood is flowing, the velocity, and which direction it's flowing in, towards or away from the transducer.
And the clinical use for that is, well, it must be massive.
It's huge. Our sources highlight it constantly. Think cardiovascular assessment detecting blocked arteries, narrowed vessels by looking at flow patterns.
Okay.
Or in obstetrics, checking blood flow in the umbilical cord or the fetus itself. It's a vital sign of fetal well-being. And vascular studies looking for things like blood clots, DVTs.
And it's non-invasive, real-time.
And incredibly safe. That combination makes Doppler indispensable in so many areas.
So beyond just adding movement with Doppler, the imaging itself is transformed too.
Mm-hmm.
We hear about 2D, 3D, 4D. What are the real differences there? What do they let us see?
Right. Well, ultrasound started pretty simply after World War II with things like A mode, which was just spikes on a line. Then came B mode, brightness mode, which is essentially what we now call 2D.
The standard view.
Yeah, 2D is your standard, real-time, flat, cross-sectional image, like taking a slice through the body. It's the workhorse for most routine exams, great for looking at internal organs, guiding procedures.
Okay, so what does 3D add?
3D takes it a step further. The machine acquires a whole volume of 2D image data, scans through a region, and then reconstructs it into a static three-dimensional image. You can rotate it, look at it from different angles.
Ah, so you get depth perception.
Exactly. It's fantastic for visualizing complex anatomy in a more intuitive way. Think looking at a baby's face in detail, or maybe planning a complex surgery by seeing the spatial relationships more clearly.
And 4D. That just sounds like science fiction.
Huh. Well, 4D is basically 3D, but in real time.
Well, like a video.
Precisely. It adds the dimension of time to 3D, so you're watching that reconstructed 3D volume move live.
Wow. What's that used for?
Dynamic assessments.
Yeah.
You could watch a baby moving the womb in 3D, or see a heart valve opening and closing in 3 dimensions, or analyze complex joint motion.
So 2D is the everyday tool, but 3D and 4D offer these extra incredibly detailed insights, either spatially or dynamically.
That's a good way to put it. They definitely enhance our diagnostic capabilities, although they usually require more advanced machines and sometimes more time.
Okay, let's shift gears a bit. For those listening who are specifically getting ready for the SPI exam, our sources were packed with some really good evidence-based strategies to, well, perform better.
Mm-hmm.
What are some of the most effective ways research actually suggests we should be studying for something like this?
Yeah, the material really hammers home the importance of active learning, moving way beyond just passively reading your notes or textbook.
Okay, active learning. Like what?
Well, 2 big ones are spaced repetition and active recall. Spaced repetition means reviewing material at specific increasing intervals. The timing is optimized based on how memory works. You revisit things just before you're likely to forget them.
Instead of cramming it all in at once.
Exactly. Cramming works for the short term, maybe, but not for long-term retention needed for the SPI in clinical practice. And active recall is about constantly testing yourself.
How so?
Using flashcards, doing practice questions, trying to explain concepts from memory without looking at your notes. It's the act of retrieving the information that strengthens the memory trace. Much more effective than just rereading.
Right, pulling it out, not just putting it in. I also saw mentions of interleaving, mixing up different topics.
Yes, interleaving. Instead of studying, say, all of Doppler in one block, then all of artifacts, you mix them up within a study session. It feels harder initially, but research shows it leads to better long-term learning and ability to discriminate between concepts.
Interesting. And using concrete examples seems obvious but important for physics, right?
Absolutely. Tying abstract principles like impedance or frequency to tangible examples like why gel is needed or how frequency affects penetration makes it stick.
And elaboration, explaining things in your own words.
Crucial. If you can explain it simply, you understand it. Teaching it to someone else, even an imaginary person, forces your brain to organize and process it deeply.
Group study can help there too, I suppose.
It can, definitely. Discussing concepts, quizzing each other, it clarifies doubts and shows you different ways of thinking about things. But just as important as knowing what to do is knowing what not to do. The sources also highlight common pitfalls.
Ah, yes, the traps to avoid, like procrastination, obviously.
The classic. But also, surprisingly, sometimes neglecting topics that seem easy or maybe boring. You assume you know them, but maybe not well enough for the exam's detail.
Good point. And just passively reading notes.
Big mistake. That creates an illusion of competence. You recognize the material, but you can't necessarily recall or apply it. And underestimating the physics section specifically is a common one for the SPI. People focus on anatomy maybe, and then get caught out by the physics.
Okay. And not practicing with actual SPI-style questions.
That's a huge one. The way questions are phrased, the types of calculations, the emphasis, it can be different from textbook exercises. Practice exams are vital.
Why are they so important?
Several reasons. They help you pinpoint your actual weak spots, not just what you think is weak. They get you familiar with the exam format and timing, which reduces anxiety. They help you practice time management under pressure. And honestly, seeing yourself improve on practice tests builds confidence.
So take multiple timed ones.
Definitely. And review all the answers afterwards, not just the ones you got wrong. Understand why the right answer is right and why the wrong ones are wrong. That's where a lot of learning happens.
Makes sense. And finally, test anxiety. It's real for a lot of people. Any tips from the sources?
Yes, several practical ones. Things like deep breathing exercises right before or even during the exam to calm your nervous system. Using positive self-talk, replacing negative thoughts like I'm going to fail with I've prepared for this, I can do this.
Visualization too.
Visualizing yourself successfully navigating the exam and the basics, making sure you get good sleep in the days leading up and proper nutrition. Don't underestimate how much physical state affects mental performance.
Yeah, those are good life skills, really, not just for exams.
Absolutely. Learning to manage stress in high-stakes situations is invaluable.
So if we kind of pull back and look at the big picture here.
Yeah.
Ultrasound's whole journey, right? From those basic A-mode spikes to the incredible 4D stuff we just talked about. It really highlights its enduring importance in medicine.
Oh, absolutely indispensable. Think about its advantages. It's non-invasive, no radiation, it gives you real-time images. It's incredibly safe, which is why it's so central to things like obstetrics.
Right.
But it's used everywhere now. Emergency medicine, cardiology, guiding biopsies. Its versatility is amazing. And the technology just keeps getting better, smaller machines, better image quality, new techniques. It's a cornerstone. It helps doctors literally see the unseen.
And for anyone listening who really wants to dive even deeper after this, our sources recommended a few key resources.
Yes, some excellent textbooks were mentioned. Ultrasound Physics and Instrumentation by Frank Meehl is a classic. Understanding Ultrasound Physics by Sidney Edelman is another highly regarded one.
And specific review guides.
The official ARDMS SPI exam review guides are obviously tailored to the test, and online platforms like Davies Publishing or Pegasus Lectures offer courses, mock exams, things like that. They are really valuable tools.
Great. So those are good starting points for anyone wanting to really master this.
Definitely.
So, okay, what does all this mean for us today? We've kind of journeyed through the basic physics, how sound lets us see. We explored acoustic impedance, that secret sauce shaping the images. We looked at the amazing Doppler effect, tracking movement,
Right.
and the whole evolution, 2D, 3D, 4D imaging. And we even got into a bit of a battle plan for tackling the SPI exam itself.
Yeah, hopefully you now have a much clearer grasp of those essential concepts, the core ideas, and also some practical strategies, enough to empower you not just to, pass an exam, but to truly understand the intricate, honestly beautiful science behind ultrasound.
It really is a field where physics just comes alive, bringing these hidden worlds inside the body to light.
It's quite profound when you think about it.
So maybe the next time you see an ultrasound image, perhaps think about that incredible dance happening, the sound waves, the different tissue properties, the clever technology interpreting those echoes. It's an amazing interplay.
It really is. And maybe consider this. As technology keeps pushing forward, maybe AI gets more involved, resolution gets even better. How might understanding these fundamental principles, the very basics of how waves interact with matter, prepare us for diagnostic tools we haven't even imagined yet? Because those basic principles, they'll likely still apply.
That is definitely a deep thought for a deep dive. Thank you so much for joining us today.
My pleasure.
We really hope you feel more informed, maybe a bit inspired by the power and ingenuity of ultrasound. We'll see you next time for another deep dive.